Welcome back to our course on Introduction to Quantum Mechanics for Computational Biologists and Quantitative Biologists too. So in the last lecture, we arrived to one of the cornerstones of this course, and namely, we sort of found a way to argue that the propagation of quantum mechanical particles, such as the electron, might be well described by a kind of modified wave type equation, which has the following structure. And it's called the Schrödinger equation. So today, we want to go a little bit deeper into what this equation actually means, both from a physics point of view and from the mathematical structure, in order to understand a little bit better all the ingredients and familiarize with them. And perhaps, if time allows us, we will get as far as deriving what is called the stationary Schrodinger equation, which is the main tool that is being used to determine electronic structure of molecules. So we're gonna sort of cover important material in this lecture. So, stick along. So let me remind you a little bit what this equation is all about. We could have started the quantum mechanical course simply by stating this equation without any explanation. No. Quantum mechanics is the fields of physics that follows from, follow the implication of an equation like this. But of course, we went a long way to arrive to this equation to gather some information about how microscopic world and macroscopic world behave differently. And one of the things that we came to the conclusion was that, the propagation of the electron occurred through a wave-like type of behavior, while the detection, the properties, when you measure the position or the velocity of the energy of the electrons, are more like particle-like. So this ingredient psi is the wave function. And it's actually the wave that describes the propagation of the electron. And remember, from the wave function, one thing we sort of imposed from the very beginning, we are interested in computing, is the probability of finding the particle at some given position, at some time, from the square modulus of the wave function. And what is the square modulus? Let me remind you from your recent lecture on complex numbers, is just the product of the wave function and its complex conjugate, which by definition is positive definite. So since this object is always greater or equal than 0, then this probability can be this quantity can be interpreted as a probability. Now, I want to emphasize that for the moment, everything that I've written here is for one particle. For instance, one electron. This same very equation can be generalized in a trivial way to include many particles, but we will deal with that complicancy later on in the course. And it will be a key complicancy because, molecules are held together by many electrons floating around. So the quantum many-body problem will be a key part of the second half, the second modulus of this course. But we are not quite there yet. Here we're just sort of taking the first kind of humble and shy steps into the quantum realm. And we try to do that in the simplest possible way, sticking to one particle. And when things get even more complicated, we're going to go even to one dimension, particle propagating on a line, just to keep things as simple as possible. So we made we reviewed what this object psi is. So let me review about everything else? Well, clearly on the left-hand side, we have a couple of constants, I and h bar. H bar is the Dirac constant. And let me remind you that h bar is actually the Planck's constant divided by 2 pi. So in this course, amazingly enough, we did not follow an historic path, which typically leads very soon to discuss what the Planck's constant is. We actually sort of very quickly glanced through it when we decided, the energy of a photon is supposed to be proportional to its frequency of the wave times the Planck's constant, which, can also be rewritten this way, but omega is pulsation, right? So one thing that should be immediately noticed here is that this constant of H is a fundamental constant of nature, because it tells us essentially how large quantum effects are. Because remember, one of the essential features that we discussed in quantum mechanics was, for instance, energy quantization, and the quanta are proportional to this constant. So when this constant becomes small, then all the quanta becomes very, very, very near to each other, or the energy difference becomes near to each other, and essentially lead to a continuum. But I don't want to enter this discussion in this very moment. I want to sort of leave this discussion for later use. I want to leave this discussion for later use, because it will become essential when we will discuss the transition from classical to quantum mechanics. However, one thing that is probably worthwhile mentioning is the numerical value of this constant in units that are typical of molecular science. So let me just do that for a moment. So if you go on my web page, let me see. If you go to my web page, and I'm going to do it here with you, go on the molecular physics, you will find a number of documents that you can download. And one is called Convention and Units. If you go down on this convention in units, you find a number of fundamental constants in some units that are typical for macromolecules. And we'll come to these units later on. Typically, the typical scale for macromolecular dynamics are the picoseconds, the kilojoule per mole, and the nanometer. Typical size of a macromolecule is in the nanometer range. Typical vibration frequencies of covalent bonds is in the picosecond range, and the typical energy is in the range of kilojoule per mole. Right? That's how do I know? Because if I could compute KT, the Boltzmann typical energy in water room temperature, is basically of order 1 in kilojoule per mole. In these units, you can see that the Dirac constants is less than 10%. It's less than 0.1 in this unit. So it's not a number of order 1 in this very natural unit. It's slightly shorter than 1. And you can already use this as a very, very sloppy preliminary argument, supporting the idea that quantum effects are not so big for macromolecular dynamics. They're probably important-ish, slightly important, but not leading. But we'll come to that later on. We'll come to that later on in more detail. So the big guy in this equation, the big mathematical mystery, is this object here. So what is H? Notice first of all that I used, well, let me use the same color. Let me just notice that I use a symbol with a hat. While everything else on this equation doesn't contain a hat. I'm gonna tell you why in just a second. So, but let me first define this guy. This is gonna be negative h bar squared over 2 mass of the particle. In 3 dimensions, I have a Laplacian, which I don't need a vector for. And then I have my potential as a function of x. So H is something that does 2 things when is applied, when sits next to psi. It transforms the function psi into another function. How? Well, fundamentally in 2 ways. By taking the second derivative, or more precisely the Laplacian, and then multiplying by this constant. And adding another term in which you take the function at x, psi, and multiply by the potential at the very same position, u of x. So let me just say it more clearly. Let's look a little bit more in detail what does this expression means. It means that you take the wave function, you take the Laplacian of the wave function, which is the second derivative in 1 dimension, but it's the sum of all second derivatives in each dimension in more than 1 dimension. And you add a second term in which you look at what is the, for each value of x, you compute u of x, and you multiply psi by that u of x. So if I look at this is a function, right? Well, what h does is acting on this function and transforming it into a new function. We already have an example of this kind of operation. Remember? If my function was a proportional to, say, something like this, well, if this is psi, then h acting on psi will be something like a, and then we get like e minus psi squared over 2m psi, which is a different function because it contains a different constant in front. Now, in this case, the new function is just proportional to the old one through this coefficient here. But if my wave function was not simply an exponential, but was like, I don't know, a sine or logarithm or 1 over x squared, whatever you name it, well, the resulting function of the action of h would have been a different function of form altogether. Okay? So h is something that operates on a function, on the function psi to give, as a result, a new function psi prime, which corresponds to a negative we'll see many examples of this. But since h is something that operates on a function to give me another function, it is called an operator. Actually, it's called the Hamiltonian operator. Okay. So we have introduced the concept of operator. Let's actually ask, what are the properties of the H operator? And let me say that whenever you see any letter with a hat, this hat here is there to remind me that this is an operator, while psi is just a function. So the symbol hat that appears in the Schrodinger equation above the H is there to remind me that H is actually a, in this case, differential operator, because it contains the Laplacian and the potential term, which is not a differential part. But what are the properties of this operator? Well, let me state them all together. Let's compute what happens if I take a function psi1. I take a generic linear combinations of two wave functions. Well, now, if you remember well, let me spell out things a bit pedantically, but there's no reason to skip steps at this level. Let me not just explicitly write the dependence on x and t of this psi1 and psi2 function. Now, this is the differential operator that acts on here and acts on there, because the derivative of a sum of function is the sum of the derivative. So since derivatives are linear operator, meaning that the derivative of the sum of a function is the sum of the derivative, and the derivative of a function times a constant is the constant times the derivative of the function. If you look at this, well, you can write this as a then negative h squared over 2m tail of psi1 plus b negative h squared of 2m gradient a Laplacian of psi2. There's a 2 here, of course. And I've taken care of this part acting here and this part acting here. Of course, now I have this multiplying this two, but now this is a simple multiplication, and the simple multiplication by a function is, of course, a linear operation. So here I get u, and I can write this as a u of x psi1 plus b u of x psi2. Then if you combine things together, you find a h psi1, because I'm combining this with this. Well, let me go back. It looks a little bit awkward, right? And b combining this together. So the result of this complicated stuff is simply h1 plus b h psi 2. So the action of h on a linear combination of function is the linear combination of the action of h on each of the function. So let me sort of write this in a single equation. What we were just discovering is these fundamental properties of the Hamiltonian operator, which follows from the fact that Hamiltonian operator is basically derivative times multiplication plus multiplication by constant, and the derivative is a linear operator, and the multiplication by constant is a linear operator. So H is a linear operator. Okay, at this point, I'd like to stop and begin building an analogy. We have other examples of linear operation in mathematics you might be aware of at this point of your course in education. In some sense, a linear operator behaves in a way that is very similar to how a matrix operates on a vector. So if I have a matrix A operating on a vector V, let me denote the matrix. Let me denote the matrix with a hat and the vector without a hat. Now we know the matrices are linear in the sense that if I have a matrix on a linear combination, we all agree that this will be a linear combination of the action of the matrix on each of the vectors. So in some sense, there is a very, very close relationship between operators such as the Hamiltonian and linear matrices, linear vector spaces, and operators on the space of vectors. We will discover later on in this course that this connection is very deep. And it's not just, it's not just by chance. In fact, you will be able to relate quantum mechanics through some procedure called discretization to a real vector space and write all the equations of classical quantum mechanics as matrices acting on vectors. But we'll come to that later on in the course. At this level, it's sufficient to notice that H is a linear operator. But it's an operator that doesn't act on a space of vector. It acts on a space of function. So let me write this. So what the matrix does, it takes a vector space, takes each and every element of the vector space, and maps it onto another element of the same vector space. This is the same vector space. And this is the vector V, and maybe this is the vector A times V. This was my vector V. You see, basically what you do, you take one vector in input, you act with a matrix on that. You act with a matrix on that, and you get a different vector, okay? And you do that in a linear way. Well, linear is defined by the properties I just discussed. Well, in some sense, the Hamiltonian operator does something very similar. You have a space of function. We will define the space of function much better later on in the course. It will be called a Hilbert space, but it's quite too early to dig into the mathematical properties of this space of function. Let's leave it for later. Let's not get too much into math at this stage. We'll get enough math as we proceed, but I have to sort of dose the amount of mathematical details in a progressive way, not to get you overdosed with math. So you take a function psi, you act on with the Hamiltonian operator, and you get a new function that you call h psi. And it's not the original function psi. It's just different one. And this new function is generated by the previous one through this transformation, which happens to be linear. So both matrices and differential operators are linear. Just to give you an idea, whenever you define a property, I think you don't understand it thoroughly until you ask yourself, okay, let's discuss something that doesn't obey that property. So let me give an example of non-linear operator. Well, for instance, you take the function psi and you define a new function psi xt squared. Why not? For example, I don't know, I could have, this is my usual plane wave function that I discussed many times in this course. And if you take the square of it, then of course you get a 2i over h bar e times t minus b. Now, it is quite clear that if you take any linear combination of this, you will not get the linear combination square. So let me say, if I have a linear combination, a psi 1 plus b psi 2, then this will become a psi 1 plus b psi 2 square, which will be a square psi 1 square plus b square psi 2 square, which is what you would expect more or less from a linear combination, with the only exception that here I don't have a and b, I have a square and b square. So it's not already nonlinear because the coefficients in front do not just add up in front. But in addition to that, you also get twice AB psi 1, psi 2. And that's, of course, nowhere close to any linear combination. So that's an example of nonlinear operator. Quantum mechanics does not involve any nonlinear operator. So the fact that quantum mechanics, well, okay. True, quantum mechanics does not involve nonlinear operator. When you will devise approximation to quantum mechanics to compute the electronic density, we will introduce at some point some method called R3-Fock, which basically can be formulated in terms of nonlinear Schrodinger equation. But let's not go into that. This is just, you'll discover what I mean at the right time. At the moment, when it comes to writing the real equation, not the approximate equation, the true equation of quantum mechanics, it is completely fair to say that there's no non-linearity involved, which is good because linear operators are about the simplest mathematical object you can use in mathematics. They have a lot of nice properties. Discussed that many times. Probably you have in your linear algebra crash course given in other courses of this mastery program. Okay, so that's an important thing. And why do I want to discuss the linearity wave function? Well, you'll be using that all over the place for the rest of this course. But let me now make one step further. And well, before we proceed, let's take another couple of examples to familiarize what does the Schrodinger equation say. So let's look at an equation. We already seen an equation that obeys the Schrodinger equation, right? That the plane wave obeys the Schrodinger equation for constant potential. So if u of x is equal to some constant, you can always set the potential energy to 0. But leave it, because the potential energy is always defined up to a constant. But let's leave it to a constant. Then we know, we have now shown already many times, that if you do this, and you act on this guy, Oh, of course, there's a Laplacian. Then you will get so let's call this psi. I get e psi. And then on the left-hand side, and then I will get like u naught psi. Sorry, that's what it is. And on the left-hand side, if I take I times h bar d by dt of psi, so this is the h psi part of the Schrodinger equation. I just reversed the order of the Schrodinger equation. I'm writing the Schrodinger equation in this form rather than the one with the orders with this term on the left-hand side and this on the right-hand side. Of course, you can always flip the orders in inequality without making any harm to the equation. So if psi is what it is, then, you know, basically, we'll discover that this is a constant times psi plus u naught times psi. So if you barely apply the Schrodinger equation to the plane wave, you arrive to the conclusion e psi plus u naught psi is equal to p squared 2m psi plus u naught psi. So these two terms cancel out, as you expected, because the equation should not depend on the specific value of the constant potential energy. And you get that this equation is satisfied as long as E is not any number, is precisely p squared over 2m. So my wave function actually should be e to the I over h bar negative of p squared over 2m t negative p dot x. So this is a legitimate solution, right? But let's already see that. Let's now imagine that my plane wave, my electron propagates not in a free space, but in the presence, for instance, of an electric field. Now, an electric field, say along the x direction, will generate a potential energy growing with x, right? So let's suppose, for instance, that my electron propagates along the x direction. And u of x is not u naught, but it's basically some constant times x. Maybe there would be like charge of the electron. I don't really care what constant it is. Let's just take a constant k times x. And we ask, is the plane wave still a solution? Of the wave of the Schrodinger equation? Let's try. We have negative s squared divided by 2m. Second derivative, this time we have to add u, which is not anymore a constant. And now, suppose this is, well, this k is actually E times the electric field, right, in the potential energy in an electric field. But let's do it in 1D for simplicity. We are not interested in multiple Ds, so this becomes multiple dimensions. For this example, this becomes a second derivative, and this becomes a simple product between, say, the electric field and the coordinate. And now let's apply this to e to the I h bar with a negative e t minus p dot x. And see if, and then we'll compare the action of this operator with the action of the I h bar times the first derivative with respect to time of this function. And we'll ask, is this an equation? Is this equation satisfied? If this equation is satisfied, then this will be a solution. If this equation is not satisfied, then psi will not be a solution of Schrodinger equation. Well, we know the right-hand side, right? The right-hand side is simply, I'm going to use it. And not, so let me call this psi. And let me write here the right-hand side. The right-hand side is going to be E times psi. Right? That's what they're built for. But now, okay, fine. I have a terrible notation. This guy E is the electric field. And this is the energy. And of course, this is a terrible notation because energy and electric field mean two different things and they should not be using the same index. So let's go back here and call this epsilon times x. So here I get epsilon to denote the electric field. Okay, now the electric field is epsilon and the energy is E, just not to get mixed up. Okay, so let's see if this equation is satisfied. I have a question mark here. So now when I act on this, I know that this term acting on the wave function will give me my usual p squared over 2m psi. But when this will act on this, it will give me E epsilon x psi of x t equal E psi of x of t. Now you see, if I close my eyes to this term here, if for a moment I pretend it's not there, I have a solution, which is the previous solution, because I have a constant on the left-hand side, a constant on the right-hand side, and all I need to ask is this constant is the two constants are equal, or stated differently that E is equal to p squared over 2m. But now this is a function of x. So depending on how where I'm computing psi, this term changes. And there is no way I can adjust the constant to make this equation to be always satisfied in all points of space. Because this term will be different at each point in space. And since it is different in each point in space, then basically I can never find a single psi such that, no, I mean, I can find a psi that obeys this equation, but it's just not the wave, not the plane wave solution that I've been trying to use and check if this equation is satisfied. So we came to the conclusion, and no, this is not an equation in general. I might find a point in which it is satisfied, for instance, in the origin, because in the origin x is equal to 0. This part vanishes, and in the origin, this is satisfied. But everywhere else in space, this is not satisfied. And an equation between function must be satisfied throughout all the support of the function, not just in a point. And so this is not an equation. I hope this example is helping you clarify what is a differential equation. A differential equation is an equation that holds everywhere in the support of the function. And so while we were very, very quick in finding a solution for the free propagating particle problem in terms of plane wave, actually we didn't have to find a solution. We constructed the Schrodinger equation such that the plane wave was a solution. But in general, given the free Schrodinger equation, you can use the plane wave and check out that it is the solution. In general, a central problem in quantum mechanics will be finding the solution of the Schrodinger equation for physical systems that are more complicated than just freely propagating particles. And in fact, Remember, a physical system is entirely determined by its Hamiltonian. So in the case of the free Hamiltonian, the Schrodinger equation is trivial. But for more complicated Hamiltonians, such as this, and there will be far more complicated Hamiltonian than this, then the Schrodinger equation will be far from trivial. And the largest part of this course will be devoted to find exact or approximate solutions of the Schrodinger equation. Now, is this an easy problem in general, or is it a hard problem? Well, this is called the Schrodinger equation again. Let me rewrite it again for a single particle. I know I'm being a little bit pedantic, but better to be pedantic than to skip on steps. This equation is actually what technically is called a partial derivative or partial differential equations. Partial differential equation, PDE. Because it's an equation that mixes up different partial derivatives with respect to time and space, plus even non-differential operators. Now, PDEs, partial differential equations, are hard. Solving PDE is a damn hard problem. Much more than solving ordinary differential equation. What is an ordinary differential equation? Well, let's go back and remember Hamilton's equations. Hamilton's equations were like, or you can simply say Newton's equation. Newton's equation was take the second derivative with respect to time of the position, multiply by mass, and equal it to the gradient. Now, as you can see here, the unknown was just r. I write very bad, my school. And so what this equation is all about is taking r, which is a function only on time, differentiate with respect to time twice, and you get the second derivative, multiply by n, and then you have to choose such r such a way that for each time doing this double differential operator with respect to time is the same as computing the gradient of the potential and evaluating the gradient of the potential with the negative signs at the position r of t, and the same r of t that stands here. Now, the important thing here is that there's only one type, that the function that you're looking for depends only on one variable, time. While the function that you're looking for here, psi, depends on multiple variables, x and t. So Newton's equation, since it depends only on one variable, the derivative is only about one single variable, these are ordinary differential equations. Versus a partial differential equation. And so the mathematical structure underneath quantum mechanics is inherently different from the mathematical structure underneath classical mechanics. And the leap from ordinary to partial differential equation is not just incremental, is a huge, gigantic jump. And as a matter of fact, you can actually invent very efficient algorithms to solve the ordinary differential equation problem, as you will see next year in Lactanzis and Tubiana's course, so that you can solve the motion of molecules, assuming that the atoms behave like classical particles for billions of small time steps, and really reproduce the motion of a macromolecules in times, maybe even predict protein folding. The problem is as complicated as that. Solving the Schrodinger equation exactly for just more than one simple quantum particle in one dimension becomes very rapidly a prohibitive problem, very rapidly, and you have to resort on approximations very soon. And this is to say that quantum mechanics, from a mathematical structure point of view, is much more involved and complicated than classical mechanics. Is inherently more complicated than classical mechanics. And that's the bad news, because was quantum mechanics simple to solve, then we would have much more information available from doing mathematical calculations of systems. But from the researcher's point of view, on the other hand, it was good news, because whenever a problem is difficult, then there is a job for a researcher. You can look at this from two sides, right? The technological sides would like the mathematics to be out of the way as soon as possible, or the scientist side who enjoys confronting with difficult problems. Anyway, we'll go into this discussion quite a lot in the future. At the moment, it's important to emphasize this deep conceptual point. So, given the fact that the Schrodinger equation is hard, can we find any way to simplify it without making any approximation? So, can we reformulate the Schrodinger problem? And by Schrodinger problem, I mean solving the Schrodinger equation. In a simpler form, that's the question I would like to address. And of course, the answer is yes. Otherwise, there will be no point of bringing this up. And I can present to you the next step in this discussion, which is the reformulation of the Schrodinger equation, in essentially two ways. I can just shoot on the whiteboard a trick, a mathematical step, and follow the implications, which is okay. That's how normally this is done. Or I can try to sort of motivate, inspire this mathematical step. But remember, anytime I do anything like inspiring a mathematical step, I'm making no real proof of that step. I'm just sort of exposing the thoughts that you might have in your mind to convince that that mathematical step ultimately leads to a simplification. Makes sense. But you could simply do that and see what happens and discover that it's a good thing to do. Right, so there's no deep reasoning in what I'm going to say. I'm going to say, okay, let's look at the Schrodinger equation. If I look at the Schrodinger equation, I know that this guy here So basically, the Hamiltonian on the right-hand side, remember the Hamiltonian is the physical interpretation of the energy, and the quantum Hamiltonian basically gives me, at least for the plane wave, it was able to give me the energy starting from the plane wave. And what this equation is actually telling me is that in order to get the energy of a plane of a function of a quantum state, I must take the time derivative. So there's a connection between energy and time derivative. So if I act with the time derivative on my function psi of x and t, basically all I do is pulling out the energy of that quantum particle. That's what this equation is telling me. Now, obviously, what I have implicitly assumed so far, which may not be always the case in making this discussion, is that the energy of the system must remain constant in time for this time derivative versus energy conversion to be universal through the dynamics. So in other words, let me specialize to the case in which my system is conservative. Now, what is a conservative system? Well, a conservative system is one in which the Hamiltonian actually reads as we wrote it. Okay, so what is a non-conservative system? Well, a non-conservative system would be one in which, for instance, the potential energy depends on time explicitly. Why? Because the energy of a particle propagated in the system, even a classical particle, wouldn't stay constant. Okay, if this is not clear to you, let's imagine a particle propagating in an electric field. Maybe maybe it's on the constant electric field that we saw before, right? And we have this constant electric field with the lines, say, operating this way. And we have an electron that is trying to go against the electric field. Now, if this is my setting, let's talk classically for a moment. If this constant electric field is uniform is there, I throw my electron with some initial velocity. As the electron moves through the electric field, it will lose kinetic energy, but it will gain potential energy. How do I know? Because it will propagate in space, and then when it will be stopping, it will go back, boom. And when it will go back on the same position as the beginning, it will have the same kinetic energy as at the initial time, because this kinetic energy was stored in the potential energy and then released back in the kinetic energy. That's an example of conservative system, right? Now let's suppose that instead the electron starts, but my potential energy changes with time. So for instance, I have an initial potential energy, I have my initial electric field, the particle slows down, and when it stops, I switch off the electric field. Then the particle is stopped, there is no more electric field, it's not going anywhere. So you see, my initial kinetic energy has been completely vanished. At this initial time, my initial energy was like completely kinetic energy, and then the final, there is no energy whatsoever. So clearly the energy of the system has changed as a result of me changing the forces in a classical setting, or equivalently to letting the potential energy vary with time. So what we are doing now is to specialize on a physical system in which the Hamiltonian is in the form that we always discussed, with a simple potential energy as a function of x and not of t. But the Schrodinger equation, in principle, is not restricted to that very situation. In principle, is still true when the potential energy depends on time. But we will concentrate on this. Now, if we concentrate on this, then of course, the energy will be constant. So I don't need, there's something redundant in this equation because, I don't need to take, I mean, I'm hand waving now. Hand waving means doing things in a sloppy heuristic way. But since the energy is constant, I expect that taking the derivative of the function at different times will always give me the same result, because it will always give me the energy of the particle. So taking the time derivative of time t, taking the time derivative of times 2t, 3t, will give me the same result. So it means that the dependence on time of the function psi is not any dependence. A hyperbolic cosine of the logarithm of sine of t. No, it has to be very specific time dependence. Psi must depend on time in a very specific way so that any time I take the derivative of psi, I get always the same result. But one possibility is, of course, the constant. Any time, and if the function psi doesn't depend on time, then any time, take the time derivative of that, I get 0. But that means that the energy is always 0, and this is not a general situation, right? So that's probably not what I'm looking for. I'm looking for a time, a genuine bona fide function of time, such that if you differentiate it, you always get the same result, no matter the value of the variable at which you are differentiating. And if you think about it hard enough, you discover that this function is the exponential, because you can get inspiration from the only solution we know so far. The only solution we know so far is the plane wave solution, which only applies to the case in which H doesn't contain any function of dependent potential energy, as we discussed. But you see, this was the time dependency This is the structure of the plane wave solution. Now, it is a very specific structure because, you see, in this particular case, the function of x of t factorizes in two independent pieces. One piece that depends on x, let me call it phi of x. Let me write it here. And one piece that depends on time, let me call it psi of time. So in this particular case, psi is a product of phi and psi. And if I act on the time derivative multiplied by h here, I will act only on the psi. And no matter what I do, I will consistently find out E. Now, the specific structure of phi is irrelevant as far as this discussion is concerned. I mean, as far as the property acting on time derivative will always give me the same result. If I want to enforce this property, I don't really need to specify what this is. All I need to have for a conservative system is that a wave function must be the product of a function of time times a function of space, and the function of time must be in the form right. So that worked for the plane wave, and we are under the impression that it should work for more general cases because the structure of the Hamiltonian never entered in this discussion we just had. Only the time derivative part of the Schrodinger equation was used to find out that the energy was always equal to the Hamiltonian on the function, right? So let's make the following intuition and say, okay, suppose H is now not the plane wave Hamiltonian, not the free particle Hamiltonian, but any conservative Hamiltonian, which means basically all Hamiltonians in which this does not depend on T. So suppose the only assumption we're making is now the Hamiltonian is in the form of the Hamiltonian we probably always thought the Hamiltonian was going to be. We never thought about putting the time dependence there. So we are not making a big restriction. For instance, electron in a molecule, they would experience the Coulomb force of the other electrons. And there will be no explicit time dependence unless I put my molecule in a varying magnetic or electric field, say I put it inside a battery. But molecules don't live inside batteries. Most of the time, molecules live around themselves with a Coulomb force, and the Hamiltonian is what it is. So by restricting ourselves to Hamiltonians in this form, we are not making large approximation. We are actually keeping most of physical systems. Now, if this is the kind of physical system I'm interested in, which again is basically all physical systems I'm interested in ultimately, except for a few particular cases, then let's assume I'm looking for solutions which have this structure. This is called an ansatz. What is an ansatz? I'm looking for solution of the Schrodinger equation, right? So my goal is to find psi, but I don't look for any kind of psi of any form. I restrict my search for the solutions to psi's that are in this form. So it's like saying, with an analogy, I know I lost my keys. And I know that I lost my keys since I was at home, because I entered home and then lost my keys. So I don't look for the keys in the car. The keys could be anywhere, even in the garage, in the car. But I have reason to believe that they are not there. So I will limit my search for the keys to the rooms in my home. Now here we're doing something about that. We're looking for a wave function psi of x and t, but for reasons that are related to the fact that we're interested in the Hamiltonian that conserves energy, I don't look for a solution of any sort, such as ones mixing t and x in weirdest ways, I should say. For example, a function of t divided by x. This is a function that certainly doesn't fit in this nice factorization, but instead, I'm looking for functions that have this nice property. Time is on one side, space is another function, they just multiply it, and the time function is just an exponential function. And I'm limiting my search to those class of functions. I'm not losing any physics because I have suspicions that this is exactly a very general thing to be doing. And there are theorems that eventually guarantees that you can do that, but let's not go into those details. So of course, I still have a hard problem because I still don't know what phi is in this equation. And I mean, I will have to fight hard to determine what phi is. But for the time being, let's suppose we leave this problem for later and see how much do I simplify the equation if I take this ansatz. Well, clearly, if I do that, this equation will be transformed into another equation. That will be E psi of x, sorry, phi of x equal h of phi of x. Why? Because this term here will produce E, and that will be, of course, in both cases, my exponential going out. You can verify this by doing explicit this time derivative. On the right-hand side, the Hamiltonian doesn't act on time, so this term will go through, and eventually I can always cancel it. So, for a conservative system, the Schrodinger equation has been reformulated in terms of a new equation, which I write in the following way. First of all, I want to emphasize that there is no time anymore in this equation. My unknown is a function of position only. So this is called the stationary or time independent Schrodinger equation. It's an equivalent formulation of the Schrodinger equation, which also is a conservative system, which does not depend on time, only on space. However, it still doesn't depend on many variables because in more than one dimension, there are more than just one variable for space. So you have derivative with respect to x, y, and z. So Hamilton's operator still is a differential, partial differential operator. What does this equation actually tell us? It tells us that I'm looking for function size such as, if I act on the function with the Hamiltonian, I don't get an entirely different function, but only the function will be scaled by a constant. You see, if I act with the Hamiltonian on psi, I don't get a different function, let's call it w. No, I get a function w, which is very specific. It's basically the original function phi stretched by a constant. So if I do the same thing, if I use the analogy with the vector space we used before, remember this is very similar to an equation which I have a vector. And after I act with my matrix on the vector, I don't get a different vector altogether w. I get a specific different vector which is proportional to my original vector. So I have my vector here. Normally, if for any v, when I act with a on v, I will get a different value, w. That's the action of the operator av. But there are some specific v's such that when I act on a of those specific v's, all I get a w, which are lambda times v. So these specific vectors such that when they are acted upon by the A matrix, you get only a constant times them. You get just stretched or compressed, but you don't change the direction. These are called the eigenvalues of A. Eigenvectors, sorry. And the corresponding constants are the eigenvalues. You should know that from your education in linear algebra. So the stationary Schrodinger equation turns out to be of the same type. It's an eigenvalue problem. I'm looking for functions now rather than vectors, such that if I act on this function with my Hamiltonian, I don't get an entirely different function. I get a constant e times the function itself. Now, in eigenvalue problems, all I have to find is the pairs of function and eigenvalues, because as you probably remember from linear algebra, I get to every single solution of the eigenvalue problem, I have the corresponding eigenvalue. So basically, this equation will not give me as a solution just psi phi and with single a, but the solution of this equation will be pairs E and phi of E of x. Eigenvalues, eigenvalue, and eigenfunction. We'll go into that much more in detail. But once you have found the solution, then of course psi of t will be built from this solution by taking the particular eigenvalue I have found, multiplied by t, and then taking the corresponding function as a function. Okay, that's quite a lot to process. So I'll stop here, and in the next lecture, we'll try to go back on these concepts and try to digest them in a very, very, very specific, very simple problem, and we'll solve our first quantum mechanical problem. Goodbye.